Good afternoon and welcome to this afternoon's Jones Seminar. I'm very happy to introduce Dr. Michael Caramanis, who is a research leader on a set of topics that have recently started being called smart grid, but he's been working in this area much longer than that name has been used to describe this area. He served on the Greek National Energy Council in the 1970s. He's worked in the MIT Energy Laboratory and was also the chair of the Greek Regulatory Authority for Energy until recently. He also co-authored a book on spot pricing of electricity, and he's now a professor at Boston University in mechanical and systems engineering. And we're very pleased to have him here today.
Thank you very much for the very kind introduction. I'm happy to be here, and I'm glad to see such a broad audience here. I was inquiring as to the proportion of female engineering students, and I was told that it's 40%. I said, gee, you're beating us. We only have 27% at BU, but I don't see the 40%. I think I was lied upon. I would like to talk to you about my current research involvement in sustainable power systems and sustainable energy and environment issues, which, of course, will benefit from advances in technology, advances in the way we approach the issue, advances in our behavior, but which to a great extent I think can also benefit from our ability to capture synergies in a systems sense that can appear and that are waiting to be used and to be taken advantage of in many of these environmentally friendly technologies and applications that we have in front of us, and which synergies can be facilitated or are enabled, although that's not sufficient, are going to be enabled by the smart grid. And I will try to describe what I mean by the smart grid, since I believe that the smart grid means many things to many people. So I want to talk about these synergies, and let me just give you a typical speech segment that I object to and which I'm going to try to address with my talk today. So very often we hear about the various solutions, the various options, the various opportunities that we have for dealing with the emissions problem, the climate problem, and so on. And as people go through down through a list, they say, okay, carbon sequestration, yes, no, maybe not, we're not quite ready, there are some problems, nuclear, this, that, and the other. The energy economy, the hydrogen economy, I'm sorry, but then they say, well, maybe in 10 years or 15 years, it's still too expensive. Then they talk about wind and solar. Solar is still on the expensive side. Wind, however, they will all admit, is quite economical. Depending on your the wind potential, you can depreciate your capital and produce electricity at an average cost of, let's say, 4 cents per kilowatt hour. That's pretty good. That's as good as coal and nuclear and so on can do, if not better. And of course, if you slap a CO2 tax on coal, it's a lot better than coal. So they say that, and then they write off wind energy with the following statement, that wind energy is intermittent, as are many of the clean energy technologies. Namely, we cannot control when electricity and how much is produced by certain assets that we have, certain wind turbines and photovoltaics and so on. We have to rely on the wind and on the sun. And although we can forecast, and we are getting pretty good in forecasting, the output of wind farms, we cannot control it. Hence, that intermittency has a very high cost, which we cannot deal with for the moment, and therefore they're not going to be a substantial solution until 10, 20 years. It's pushed out into the future. I'm going to challenge that and claim that with a smart grid, with our ability to adapt consumption to supply, we can deal with this intermittency and lift some of the barriers by exploiting synergies between certain types of loads, such as the electric automobile, which will provide a load that has characteristics and capabilities that are quite different from that of other loads. So if we capture the synergies between these new loads and these new sort of sustainable energy technologies and intermittent generation, we can lift some of the barriers that exist and which might delay adoption of these technologies for quite a while. And you should all know as engineers that a great idea is very often not adopted for all sorts of reasons that have to do very little with the merit and the efficiency of the technology. You probably all know that television stayed in the shelf as a discovery for quite a few years, almost 10 years, until RCA picked it up. So we don't want to have all of these good ideas stay in the shelf for another 10 years, because unfortunately we're in a hurry. We're in a hurry to do something about the environment and to control emissions. So I'll briefly try to present a number of issues, say something about sustainable energy future. I will describe my notion of the physical energy grid and the smart grid, and what is a smart grid in relationship. Describe certain idiosyncrasies of the electric power system. And by the way, I'm going to argue that electricity is very important to a sustainable environment, a sustainable energy future, because you probably remember from your thermodynamics that it has a much higher work availability than other forms of energy, and because all the new energy technologies are more or less playing through electricity. So you all know that we can, through heat pumps, electric heat pumps, we can produce up to 3 or 4 times as much heating and cooling than burning fossil fuels, and hence electricity can contribute to conservation, and also, of course, it can contribute to adoption of new energy technologies. So, but it has an idiosyncrasy, which is one that requires reserves, capacity reserves, to make the system secure and sustainable. So I'll talk a little bit about this, and then I will introduce synergies, of intermittent clean energy technology generation, and load participation into the market, including hybrid electric vehicles, and conclude with a study that I've made as to how appropriately managed electric vehicles can achieve a fair amount of these synergies. And there are some technical issues that I'll probably skip over at this point. So I've already put a plug into electricity. It's very important because it can give us higher efficiencies through waste heat recovery and use of heat pumps, appropriate use of heat pumps. Then if you look at the contributors, the many contributors to CO2, to greenhouse gas emissions, then you see that the electricity sector, at least in the United States, these are figures for the United States, the electricity sector through our coal plants and so on, primarily our coal plants, generating plants, and other fossil fuel using plants contribute about 1/3 of the CO2 emissions. And you can see here these are millions of tons of CO2 per year. Then our households contribute more or less another 1/3, and direct uses of fossil fuels. We burn fossil fuel to make steel and create heat and so on, in addition to heat our home. And finally, the last 1/3 comes from the internal combustion engine, right? Of which there is very little talk. We talk about cap and trade, but we don't talk very much about doing something about the internal combustion engine. Of course, we talk about improving efficiency, et cetera, et cetera. So the ultimate improvement there would be to electrify the transportation sector, and that's a technology that's more or less at the verge of being widely available and fairly economical. Hydrogen may do this, but it's still too expensive. We need more research, and material scientists, chemical engineers, and mechanical engineers have to invent new technologies to be able to decrease the cost of creating hydrogen and using hydrogen and storing hydrogen and all of that. So therefore, using electric vehicles, hybrid electric vehicles, is one option for addressing this 1/3 of the emissions, provided, of course, that the electricity that we use to charge our vehicles doesn't come from more coal plants, but it comes from renewable technology, right? And that's why the two are coupled. And I'll maybe during my talk or during the discussion give you some political and other sort of non-economic issues why this synergy is important. So what is important, what is strange about electricity? So the power sector is, or the power system, today's power system, is the largest machine that humans have made. Why do I call it the largest machine? Because every generator is more or less connected to every other generator, because all generators have to be synchronized in feeding their output into the transmission network. So if you think of all the hundreds and thousands of generators that inject electricity into the transmission system, together with the transmission system, with the distribution system, and the consumption at our homes, with all of our appliances and so on. This is a huge machine. It's the largest machine that humans have ever made. So, but that system needs to remain synchronized. It needs to balance supply and demand almost in real time, essentially in real time, within milliseconds. We have a little bit of play, but essentially there has to be a real-time energy balance. And there are other sorts of congestions that we have to deal with that have to do with the way we transport electricity, electric power, and there may be congestion in our highways, which is the transmission system, the high voltage system, and congestion in the local streets, which are here the distribution system. So that congestion has to be managed in real time, and it has to be managed in the presence of uncertainties. What are uncertainties? A power line may be disconnected because of thunder, because of some relay disconnecting it. A power plant may fail, may be forced out. Demand may change in an unpredictable fashion. So all of these uncertainties make the task of managing the security of the system much harder. So I remember when I worked in the area of, on the question of could markets with many participants play an important role, that was in maybe in the early 80s. All the utility people who were on the other side of the debate, and utilities then were vertically integrated. So a utility was generating, transmitting, distributing, and worrying about serving retail loads. So these utilities said you can't introduce markets, you can't unbundle these functions, any of these functions, because how will we be able to maintain the stability of the system? We're going to have blackouts all the time. And of course, markets did go forward, but in a slightly different manner that we envisioned it at the time. So the first massive market was created in England in 1990. National Grid, which you probably know as a distribution utility these days, because they've come and they've invested in distribution in the United States, was a company that was created to manage the transmission system in England and separate, unbundle the transmission system, which is a natural monopoly and cannot be subject to competition. You can't have different lines competing, but which then allowed competition on the generation side and competition on the retail side through free third-party access to the transmission network. So all of a sudden, if you wanted to build a power plant, you didn't have to ask permission from, before you couldn't do it, because all power plants in a natural franchise, you know, in Central Maine Power's, for example, territory, had to be owned by Central Maine Power. So now individuals could build generators and have access to the transmission grid, and retailers could buy from the transmission system, have access to the distribution system, and serve homes. So, so markets were created, but the only way that markets could work was to realize, and that's very important, and that will allow me to go through the next slides faster, was to realize that electricity is not just one product, but it's a basket, it's a bundle of products. So we don't just buy energy, but we have to buy energy, and we have to buy reserves, capacity reserves, and there's not one capacity reserve, there are many capacity reserves that, you know, one that that has to be able to respond very fast, or fast, you know, super fast, fast. simply fast, and so on. So time scales are 30 seconds, 5 minutes, 15 minutes, and longer. Right? So these reserves can now be purchased and procured in the market. Right? So in the market, you buy energy if you are a consumer, you sell energy if you're a generator, but you also, if you are the market operator or the independent system operator, so in New England we have the New England ISO, the New England Independent System Operator, who schedules the generators and buys energy through some sort of a stock market or an energy market that clears prices at each hour, and then on the hour, and then real time for every 5 minutes, but also procures reserves. And the difference, so these reserves are bought and sold through the market. There's a clearing price for them as well. So it's not just energy. There's energy, there's a clearing price for super fast reserves, frequency control reserves, for fast reserves, regulation service or secondary reserves, and spinning reserves or operating reserves, which are the 15-minute reserves. So the New England Independent System Operator buys all 4 of these things. And there's a clearing price for each one of these 4 things, products. And then he can use these reserves, right, on command, and maintain centrally, in some sense, the security and the safety of the system. So that was how markets were able to work, right? And all the sort of objections of people against it were met to the extent that they were sort of rational and did not hide an agenda, did not have a hidden agenda behind them. So we have markets. These markets are not complete because not everybody is able to participate in them. And the reason is lack of information and so on. Only the generation side, only the centralized resources can participate in it. So this market is incomplete. And there's absolutely no market at all at the distribution level. This market operates wherever it does at the transmission center level. So what is the smart grid? So a broadly construed version of the smart grid would be a notion of the smart grid which could be named, and I'll tell you why, as a cyber-physical system. Those of you that are looking for research opportunities, you'll see that the National Science Foundation, National Institute of Standards, DOE, and so on, are often talking about the cyber-physical system. What is this cyber-physical system? The cyber-physical system is, on the physical side, something that contains all the hardware, generators, buildings, real estate, copper wires, towers for transmission, transformers, distribution lines, the meter at your home, this meter that rotates and measures how much electricity you consume, then the circuitry in your home, and all of your appliances. That's the hardware. That's the physical part of this cyber-physical system. What's the cyber? The cyber is all the intelligence, the automation, the software, the decision support, etc. that goes with it. So this cyber and physical portion makes up a platform, which we call the cyber-physical platform. It's the smart grid, broadly construed. And the idea is that in this smart grid, we should be able to have, to the extent possible, open participation of various actors. Let me talk a little bit more about the smart grid and also at the same time give you some idea of the order of magnitude of costs that we are dealing with when we look at the various, at some sort of an unbundling of the various physical with their cyber capabilities, components of the smart grid. So if you look at your electricity bill, I don't know if you have unbundled bills up here in New Hampshire, but in Massachusetts we do. I believe you should have here as well. You see the total bill that you have to pay. And then you see that it's made up of two components. One component is called the energy cost, and the other component is the delivery cost. And if you look roughly, you'll see that the delivery cost is about 40% of the total. Right? So if your bill is $100, maybe $60 is the energy cost, and $40 is the delivery cost. So this is an unbundling of the costs, which more or less maps into what I'm showing here. So 60% is roughly, of course it varies, right? In real time it varies and so on. It varies from various places in the United States. But roughly the average for the United States is like this. About 60% of the cost of electricity as it is charged to you, that's delivered to your home, to drive your lights, your toaster, what have you, goes to pay for fuel costs, for operation maintenance, and for servicing the capital of big generating units. So it's about 60%. The transmission system, those big, tall towers that are very important and which make the sort of the backbone of our transmission and distribution system, cost 5%, maybe 7, maybe at most 10% of the overall cost. And then, and this is something that we have not realized, or that we don't often realize, not that we haven't realized, but most of us don't realize, 30 to 40% of the overall cost is associated with the distribution lines, the maintenance of the distribution lines, the transformers that transform electricity from high voltage to medium voltage and then to low voltage so that you can safely and securely use it at home without being electrocuted. And the losses. Most of the losses, the transportation losses, do not happen at the transmission system. There we have maybe 0.5% to 1% of losses, because if you remember, your electricity losses are proportional to the square of the current times roughly something that looks like the resistance. But power is equal to the product of voltage times current. So if the voltage is very high, right, if it's 600 kV, then the current is very little, and the losses are very low. So therefore, the transmission system is responsible for 0.5%, 1% of losses, 1.5%, depending on where you are. However, the distribution system is responsible for, on the average, losses of 8%. On the average. But at night, that's maybe 2 or 3%. During the peak hour, it's maybe 12%, 13%. And remember, losses are equal to current I squared times some constant, resistance. Right? How about the marginal losses then? So if the average losses are, say, 10%, 12% during an hour, right? The average losses are I square R. If I divide by I to find per unit of current, right? Losses. The average losses are I times R. How about the marginal losses? Just try taking the derivative of I square R. What will you get? 2IR, right? So this is twice the average losses. which means that when the average losses during an hour are 12%, your marginal losses are 24. You consume 1 kilowatt hour, you need to generate 1.24 kilowatt hours out there to make up. So the costs are very high on the distribution system. And hence, having cost-reflective rates at the distribution level, which means establishing a market, just like we have for the wholesale. At the wholesale level, electricity prices change over time and change by space. So there's a different price here than there is down in Connecticut. And there's a different price at noon than there is in the middle of the night. But at the distribution level, we just see an averaged flat price, right? Markets do not exist, do not convey, they are not cost reflective. Now, to make things better, what do you need? You need more intelligence. And here my check marks are sort of a rough grading of the intelligence in this cyber-physical type of view of things, of various components of the smart grid, the broadly construed smart grid. Power plants are pretty sophisticated. They have automation, they have governors, they have automatic generation control, they have all sorts of things, they have relays that disconnect them so that they are not damaged, and so on. The transmission system, including the transformers at that level, also have a fair amount of intelligence. The cyber component, it's pretty high. We have the SCADA systems that we've had them for quite a while, which allow us to have situational awareness, allow us to know what is happening, what the flow is, what the losses are, what's being overloaded, etc. Now we can do better by adding more Phasor monitoring units, and that's the big addition that the smart grid is going to bring about. And what are those? The Phasor monitoring units are units that monitor phase differences between voltage and current, and between voltages and so on, between voltages particularly at different buses, and allow you to intervene if there's a big disruption and avoid losing the whole system. A big disruption, let's say in Florida, may create problems that propagate all the way to Canada and back. And you may get a blackout if you do not intervene. So these PMUs will be able to handle that much more efficiently and make investments unnecessary. However, at the distribution level, we have a big lack of intelligence, bad luck. We run out of luck there because of the lack of intelligence. So we don't have smart meters. We don't have sensors that can tell when a transformer is heating up and is about to burst, and when a distribution line fails, we have to send out crews to start from the two ends and start working to each other to find where the fault is, and so on. And primarily, we cannot monitor the time behavior of consumption at the various consumption points, nor can we monitor losses as they prevail in various points of the distribution network. And this is why when people talk about the smart grid, almost uniformly think of smart meters, right? So what if I had smart meters that were able to measure how much you're consuming when, and so on. So then I might be able to give you some more cost-reflective rates and make you behave more efficiently. So these are the basic issues, and you can see that the creation of markets that deal with the generation, the centralized sort of portion of centralized generation, have become a reality, and they have achieved quite a lot of efficiency gains. However, there's nothing at the distribution level. There's nothing at the distribution level. Now, another development at the distribution level, which is very important, is that there are transformative changes taking place with distributed generation. So what is distributed generation? We are used to centralized generation, right? Big power plants generating, and power flowing from them to our homes. But now, distributed generation is becoming a reality. Distributed generation means having rooftop photovoltaics. Distributed generation means having small wind. Distributed generation means having heat pumps and low enthalpy heat pumps, exploiting heat pumps at your home. Distributed generation and distributed resources means having storage at your home in terms of batteries or flywheels. Distributed generation and resources means having electric automobiles coming into your garage and plugging in to require electricity. And when they plug in to require electricity, they require energy. They don't require capacity. What's the difference? If you plug in your hair dryer and you need to go out, the hair dryer needs to dry your hair in the next 10 minutes. So you require 1.5 kilowatt, 2 kilowatts, if it's a big hair dryer, right then and there. I can use half a kilowatt. I don't need a hair dryer, so I'm good. I'm good. I'm a responsible citizen in this sense. But I wish I had use. I wish I could have use of a stronger hair dryer. Unfortunately, I don't have. So that's demanding capacity. When you plug in your electric automobile with appropriate smarts, a smart interface, and somebody who can manage how you load it, the only thing you say is that here I am, I'm plugged in, I need so much in my battery can accommodate so much, and I'm going to need my battery charged in 5 hours, 10 hours. That's a different type of load. That's a fundamentally different type of load, which can be used synergistically to take the slack of the intermittency that we talked about. So we have to be able to deal with the flow of energy in both ways, and that's what the smart grid will make possible for us. And that imposes very important technical challenges in addition to sort of economic and systems challenges. What are the synergies that can be realized by the CPS platform? What's CPS? That's a Cyber Physical System Platform, right? Remember, that's all the hardware and the intelligence and so on, starting from the generator, going all the way to your appliance. And by the way, what's missing in terms of intelligence at the distribution level is advanced metering information, system identification, in other words, sensors that tell you about losses, about heating transformers and so on, the ability to dynamically reconfigure the distribution grid. So if a particular transformer is overloaded and it's using up its life expectancy or is about to burn, you reconfigure and you send the load to other ones. And GFAs, these GFAs I wanted to talk about, are very important. What are the GFAs? These are grid-friendly appliances. And there are a lot of studies that for example, the National Institute of, the National Laboratory in the Northwest has been doing studies about, and others, there are other experiments. Excellergy in Denver and Colorado are doing experiments, and Google and IBM and so on. So the GFAs are gadgets that you can add to your appliance. And GE is interested, of course, in them, and others. You can add these to your electric hot water heater. You can add these to your washer. You can add these to your refrigerator, and so on, to your air conditioner. And have these appliances respond in a friendly manner to the needs of the grid. For example, if they detect frequency falling, they say, there's a problem. Where am I on my band? Am I below the upper dead band of the thermostat? If I am and I'm operating, I better shut off. Right? Sort of things like that. So automatically, without your involvement, they are friendly to the grid. So this is all part of the smart grid investments that are needed, and some of which are on the utility side of the meter, some of which, as you can see with grid-friendly appliances, are on the customer side of the meter. These are in your home. So, what are the synergies that this cyber-physical system platform can achieve? Let's look at all the let's look at all the clean energy technologies, including, by the way, nuclear. And I know nuclear is not very popular. It's not popular with me, but it's an important way to generate clean energy. So nuclear, wind, solar, and so on have something in common. What do they have in common? What they have in common is a limited flexibility, limited ability to control their output. Nuclear power plants have to operate flat. Maybe you can modulate them a little bit, but you cannot use them to follow the load. You cannot use them to increase their output during peak hours and decrease it at other times. And of course, clean energy technology is much more intermittent in the sense that you cannot control the output. So one way of allowing us to use more of these clean energy technologies, which suffer from intermittency or lack of flexibility, is to adapt the load side to the supply. So our supply, our clean supply, is not as controllable. We don't throw our hands up and say that, therefore, we have to wait another 20 years before we play with them. But you see to it that load, you see to it that load is responsive to this intermittency, so in essence, we don't want to flatten load, which you may have heard about as being an objective, but we want the load to be variable, but to have the negative variability of supply and of generation. And I'm going to finish in about 5 minutes, having covered only a small fraction of my slides. But I think I've touched upon most of the important issues. Let me say the following. Load, the way we know it, is very difficult to respond. Why? Well, some of our loads are capacity loads, right? So we need it right then and there. We can't delay studying. So we can't say, okay, I'm going to turn off my lights now and get up at 3 o'clock in the morning to study, because then the electricity is less expensive, right? So these loads you can't shift around. You cannot reschedule easily, right? But, and you're not going to bother to reschedule them. Nor are you going to possibly say, well, I'm not going to run my dishwasher now, I'm going to wake up at 3 o'clock in the morning to run it. But many of these you can live up to some automated, some intelligent, some cyber capability that follows your instructions and observes your preferences to do. So you don't have the transaction costs, as we say. You don't have the cost of having to worry about these things. Although Google now is allowing you to be able to remotely observe all the appliances at your home, and from wherever you are, right? You are in the coffee shop, studying, chatting, whatever. You can shut off this, turn on that. Okay, so that's great, maybe, and that's a wonderful sort of new attitude that's capitalizing on people's environmental conscience. But I don't think it's something that we can count on being adopted by everyone, right? It's a fashion. Even if everyone were to become an avid environmentalist, would probably tire and stop doing that, right? It can't be an obsession. I mean, you could from your iPhone, you could all the time. I mean, you guys, you play with your iPhones all the time, right? Or your smartphones. So, but we can't count on this being adopted by everyone and being sustainable, right? It's difficult, it's costly to have to worry about these things. So you can automate them. But most importantly, there are other loads, such as the charging of batteries, which are very benevolent loads, which are loads that are uniquely qualified for actually doing this complementary behavior. So in order for this to happen, you have to have situation awareness. You need to know what the costs are, how the costs are changing. And you need to allow for either automation or specializing entities, firms, companies, load aggregators as we call them, that actually assume the burden of managing loads. There's a very successful such company which has been founded by 2 Dartmouth graduates, alas not engineering graduates, but tech graduates, which is called Enernoc. So Enernoc has been experiencing huge growth. It's still not quite on the black yet because it's expanding. It's investing on customer side of the meter cyber intelligence, which it is not whose cost it's not recovering right away, but it will recover it over time, and which is managing loads. It's managing loads to the extent that it has control of enough loads that allow it to be able to deliver a country almost 2,500 to 3,000 megawatts of capacity up or down. So these are the sort of operating reserves. The New England Independent System Operator calls them up and say, deliver to me 400 megawatts for an hour and a half, or 2 hours. They do it. And they are able to respond within 15 minutes. So they call up, they communicate. I mean, if you go to their control center, and I encourage you to do so if you're down in Boston. The control center in Boston, they have a backup one in San Francisco, is a huge control center with people with big screens where they see dots of loads participating in that scheme. And of course they make money because they sell that service and they share their income with the participating customers. So EnerNOC is doing that. It's a load aggregator. So automated equipment, people's attitudes, grid-friendly appliances, and load aggregators that do this load management are I think, the future. Electric automobiles can provide a huge such capability. And let me finish by saying the following. So if we were to have, what was the American dream? One car in every garage? Two cars and a chicken in every pot? Okay, so we'll continue with the chicken. No, do we have, yes, white meat. Chicken on every pot, but 2 electric automobiles on every garage. So if you have total transformation, if you were to have a total, which will take place over time, right? We turn around 10% of our autos every year anyway. So if we were to only build electric or hybrid electric, in 10 years we could have. But of course it's not going to happen in 10 years. Say in 15, 20 years, maybe 10 years we can have 20% of the cars, 20, 30% of the cars. So these cars can now provide the type of reserves that EnerNOC is providing, and the more valuable and expensive reserves which are associated with regulation service, and which is exactly what you need to deal with wind farms. And here's what happens with wind farms. If we have wind farms, right now we have wind farms that generate about 2% of our energy. Their nameplate capacity is about 4% of our installed capacity. They generate only 2% of the energy, of course, because they don't operate for all the hours, right? The year has 760 hours, and they have maybe 4,000 equivalent hours. So our experience here and in Europe, where this 2% capacity, 2% energy, 4% capacity is something like, in Denmark, it's 20% of the energy, 40% of the capacity. In Spain, it's about 15% of the energy, 10-15% of the energy, 20-25% of capacity, namely wind. It's wind. So we know that we can predict the output of wind and therefore schedule around not only the centralized fossil controllable generators, including hydro and all of that, but also schedule reserves and schedule demand accordingly, right? So on a day-ahead basis, and the way markets operate today, I think I mentioned it, is that you have bids and offers from generators and consumers. You'll have for more consumers and smaller consumers. Right now, most of the bids on the consumption side is only for energy, and it's unpriced, which means that I want this energy regardless of the price. And by noon of the day before, there's an auctioning, and there are market clearing prices for every hour starting at 12 noon, 24 hours. That's the day ahead. And then you have the adjustment markets, which are similar kind of things that happen a little bit later after some uncertainty has revealed itself. And finally, you have the real-time market, which is an every 5 minutes clearing of prices. And these new prices you use to charge and debit for deviations from what was bought in the day-ahead market. So it's almost like financial markets. You hedge on the day ahead, and then in the real-time markets you adjust, and you may decide to consume more, generate less, etc. Now, and the same thing for the reserves. right? So on the day ahead, I can predict my wind generation for every hour of the 24 hours with an error of 20%. So standard deviation is this, let's say 2 standard deviations. Standard deviation is about 10% of the expected output. Right? So we are very good in predicting. And then an hour ahead, I have a 2% standard deviation, 2.5% standard deviation, therefore 5% error, right, with 2 standard deviations. So they have 90-something%. So that means that tells you that this 5% is proportional to the additional fast reserves that I will need. Right? Because if I can't predict the output with better than 5%, and you know, when it comes to predicting the output over the hour, the average, that's we do a little bit better. If we are interested in predicting the output over the next 5 minutes, right, then that's a little bit harder because there's less averaging, there's less law of large numbers. So for every nameplate capacity quantity that we install on wind, we need about 5% of that of fast regulation service, you know, ability to respond within 5 minutes. And that's what a recent study of the California independent system operator, CAISO, has come up with. There are other studies of G and so on that say, G, no, we don't need as much, but that's because, if you read carefully, that's because they assume that you're going to disallow wind farms to generate. So you can't harvest fully. If you can't harvest fully, if you don't harvest fully the potential output, then you can do with less. So we need about 5% reserves, regulation reserves. We did a study that I'm not going to go over, which looks at charging batteries, looks at when cars arrive, when they want to leave, what the cost is of energy and of regulation service throughout the day, throughout the night. And our study comes up with some component of the cyber part of the smart grid, which is a decision support that tells you every hour, every 5 minutes in the real-time market, how much energy you should buy for sure to charge your batteries, and how much energy you should try to buy but make it subject to regulation service, to going up and down if needed. Right? So the clearing prices are quite comparable. So therefore, for the portion that you sell as regulation service, you'll have a cost that's almost zero. That's 10% of the cost of the for sure energy that you buy. Now, of course, you have some costs associated with that. What is the cost? The cost is that you have to make sure that the distribution network has enough capacity in the feeder line that comes to your garage that allows you to double the consumption, right? Because if I sell 50 kilowatts of regulation service, that means that I have to be charging car batteries at 50 kilowatt rate, and then on demand by the utility, I can increase this to 100 or drop it to 0. To increase it to 100, that means that I have to have another 50 kilowatts of feeder capacity, right? That comes to my garage. Right? So I have to sacrifice, I have to sort of bargain that capacity. Anyway, so we did a study, and our study shows that on the average, you can provide maybe 10 to 15% of your energy, you can get it by providing regulation service. So that's almost equivalent to the regulation service that you need in order to increase the supply of energy from intermittent. So all electrification of the transportation industry means 30% increase of loads, means if you want to produce this energy by wind, means the equivalent amount of wind being installed, right? That will increase the need for regulation service. So therefore, wind farms would never be adopted if we could not find the cheap regulation service to deal with their intermittency. And that would be a showstopper. But if the electric automobile also makes its way in some sort of a synchronized, roughly synchronized fashion, then the two of them together can deal with the problems, right? So that's the issue. And finally, let me stop here, and you may want to ask me what the political issues are behind that. I'm not going to say that. Only if you have some interest. And you are right that I overshot.
We have time for some questions.
So we just completed a study on smart grids. We were working for a communications company, and we spoke to about 30 or 40 utilities. The biggest concern for us was that the level of planning is so different.
The level of?
Planning. Like you can say the level of smartness that they want to achieve is so different. And also the costs related to their level of planning will also differ so much that through the grant system, which is the grants which are being issued out, the who get the grants are in a really good position to implement these smart grids. But what about the ones which don't? Can we have uniformity with this sort of system?
Well, this is why it's very important for the smart grid to be open to users and developers. Because utilities should not be the exclusive developers of the smart grid. Why? Because if we give exclusivity to the development, the developer will either look for its own interests. So for example, a utility right now, a distribution utility, how does it get its income? It gets its income from being able to charge an average price per kilowatt hour consumed. Fine, it's the same in New England, in California, and so on. You have Southern Cal Edison coming up and ringing a big bell and crying bloody murder and saying, gee, you know, with this net metering rooftop photovoltaics, I have a few thousand, 15, 20,000 households that are showing a net consumption of zero, right? Net consumption of zero. The regulator has allowed me for the distribution system, which these guys use. They use the distribution system, right? They have allowed me to charge 3 cents per kilowatt hour. These guys are, now these households are consuming zero. Therefore, I'm not, you know, I'm still maintaining the connection to their home and so on and so forth, and I'm getting zero. And they may be right, they may be wrong, because the behavior of the rooftop photovoltaics may be decreasing their losses and so on disproportionately to the losses that when the flow is put. So there are varying interests, number one. And number two, there are benefits that not everybody can see. Right? The utilities see, what do they see the benefit for the smart grid? Being able to monitor their transformers, maintain their system, identify failures, interruptions in the lines, and so on and so forth. Right? They're not particularly interested in dealing with load management. General Electric, which is interested very much in technology that's on the smart grid. You know, we had the Ecomagination president talk at BU in our presidential energy lecture series, and had dinner with him. And he said, look, we at GE, we are a technology company. We don't care about this labor-intensive business that you're talking about with load aggregators and energy service companies like Enernog and so on. managing loads. We don't care. We don't care. Of course, they then had second thoughts, because then my sort of argument with them was, okay, you don't care, like you don't care for providing such services to generators, like to electric utilities that buy generators. I said, sure, we only care about selling generators. But then why do you have a big group that provides support? They say, but this group is not a money-making group. Aha, he says. But we have it because of the so-called dual markets. Because we don't make money from this, but the utilities see a bigger value added for their generators, and they buy more generators. So anyway, so of course they should be interested. That's why we're saying that the platform should be open to competing developers and users. So ENERNOC right now is developing smart grid type of things. They're not a utility. So I agree that the utility may have different priorities.
So ENERNOC currently plays on the generation side. The market they play is the core capacity market. That's sort of integrated with generation. You're envisioning a totally new market on the distribution side, and how does that form? How close are you to it?
It's not totally new. So you have the wholesale markets, and I'm envisioning the demand side loads participating in the wholesale markets, and a new market developing at the retail distribution level where distributed generation and demand participate. The participation of the load side at the wholesale market is not totally new. Some consumers are participating in the market. They're buying energy. How about reserves? There's only one wholesale market, the most advanced one and the biggest one, PJM, which is Pennsylvania, Jersey, Maryland. They have about 170 gigawatts of peak load, or of installed capacity, maybe their peak load is the same order of magnitude. The installed capacity is probably 10% above that, right? Because you need some reserves. And in the summer of 2006, they changed their rules. They renamed spinning reserves to operating reserves, and they allowed the load side to participate in the market and sell reserves. Thriving market, and the jury is in from the point of view of their ability to be reliable. They are responding at a 97% rate as opposed to 93 to 92% rate of generators. So generators are not always able to provide what they promised, right? So they are able to respond 92, 93%. The load has been able to respond at a much higher rate. So it's doable, it's starting. At the distribution level, you can't do it if you don't have the information, right? If I don't know when I consume, et cetera, you know, how can I participate in the market? Unless ENERNOC comes in and puts the verification and the measurement equipment, and essentially the service that ENERNOC is, one of the important services in addition to communication is being able to verify that you actually dropped load. Because you cannot verify that from the meters. They're not time sensitive.
I'm going to suggest that we take further questions down here informally, and thank Dr. Caramanis one more time.
Thank you.